And last time we got into titrations. And we were talking about a specific type of titration, which was a strong acid and a strong base titration. And again, in this titration, you are adding the base to the acid. And we talked about titration curve, and titration curve looks something like this, volume of base. And it gives you kind of that S type of shape. And we have our equivalence point there. And remember that the equivalence point is the point where the moles of the acid will equal the moles of the base. And there's really, as we talked about, sort of 4 spots on the titration curve. There is sort of the initial here before you start titration. There is once you start the titration to the equivalence point. Obviously, the equivalence point is the 3rd spot. And then there's also past the equivalence point, sort of the 4th part of the titration curve here. And we talked about sort of how to figure out the pH along this titration. And remember that originally here in this type of titration, before you begin adding any base, you pretty much have just a strong acid. And because of that, you really could go right into the pH equation at the very beginning here. Once you do start the titration, as we talked about with buffers and also with titrations, you are adding volume, which means you do need to do an ice table. And that ice table should be done in moles, again, because you are adding volume. At the end of that ice table, you should convert back to molarity. And the change in this part is going to be the base at this point, because it's kind of the limiting reagent. We haven't got to the equivalence point where they're equal. So the change will actually use a number and not an X in this case, and it would be the moles of the base. You would then want to convert back to molarity, like I said, at the end using the total volume. And really what you should have left over at that point, once you do that, is still a strong acid. And that means you could then just go into the pH equation at that point. In this type of titration, once you reach the equivalence point, as we talked about, it is where the moles of the acid and the moles of the base equal each other. You essentially will have only a salt left over, and that salt did come from a strong acid or a strong base and a strong base, which means it will not go through hydrolysis. And because of that, we would expect in this type of titration, our pH at the equivalence point to be neutral and 7. Once you go past the equivalence point, again, you need to do an ice table in moles. Here, though, there is a switch of what happens. So at this point, the moles of the base that you're adding is more than the moles of the acid you started with. So the acid actually becomes sort of the limiting reagent, and the change is the moles of the acid. And what you'll be left with, obviously, after you do this one in moles, is you will be left with basically a strong base left over. And that strong base will get you to the pOH and then to the pH as well. Now, we also talked about this, very common to see as you approach the equivalence point. We do see this kind of vertical rise in the pH before the equivalence point and also after the equivalence point. So as we talked about, that's really why, for example, you do see your indicator change a big in terms of color, as it does not take a lot of volume once you get near the equivalence point to change the pH a lot. And since the indicators work off of a pH range, by just adding a drop or two over the equivalence point, you actually can be a much higher pH and see a darker pink color, for example, if you use a phenolphthalein in that case. So we typically do see, again, both of those sort of rises to the equivalence point and then past the equivalence point, and then it will sort of mellow out there towards the top. Any questions on any of that there that we talked about? All right, so we're going to then continue on and talk about the next type of titration. And the next type of titration It's going to be a titration of a weak acid with a strong base. So in this case, something like acetic acid, which is a weak acid, and sodium hydroxide, which is a strong base. And again, that's going to give us some sodium acetate and some water in this case here. Now, in this case, the orientation is very similar. We will have the base added to the acid. So again, we are adding base to our acid in this case. And that's what we see here. We see kind of a low pH to a high pH. So it tells us we are adding base. We also see that perhaps our pH starts a little bit higher because we do have a weak acid that we're starting with rather than maybe a strong acid. We do see the same sort of typical S curve, and there is the same sort of 4 parts to this titration curve. Again, we have kind of before we begin the titration, we have once we begin to the equivalence point, third stop there is the equivalence point, and then past the equivalence point, once again, is sort of the 4th part of this titration. So we're again going to kind of go through each of the parts here and talk about what is happening and sort of the calculations that you need to do. So we'll start again here with the first part, and we'll go this way maybe here. There, that worked. I think, yeah. So at the very first part, before we start, before any sodium hydroxide added, really at the start of the titration, we just think about what we got going on. We basically have our weak acid there, right, in the beaker. And if we want the pH of our initial solution, because this is a weak acid, it will break apart into H plus and acetate and will set up an equilibrium because it is a weak acid. And that means if we want kind of our opening pH here in this type of titration, we would have to do a weak acid Ka type of problem. So we would need an ice table, which would make something like this. And because we have not added any base or sodium hydroxide in this particular example to our beaker yet, we can actually just use our initial molarity here. So we actually don't need to do this first table here in moles because we haven't added any volume or anything like that. This is going to be just a typical Ka type of table with some zeros, some X's. Yeah. Initial minus X, X, and X. Just like normal here, we would go into our Ka expression. That would equal something like 1.8 times 10 to the minus 5, perhaps. Obviously, here we would solve for X. And again, you could do an assumption if it works. Quadratic, probably an assumption might work. And once we solve for X, we can see again from our ice table that X would equal the H plus concentration, and then that would allow you to get to the pH. So you can see that this titration is a little bit different than the previous one, where we're starting with a strong acid, and all we have to do is just go right into the pH equation because it is a strong acid, it's going to completely dissociate. Here again, we have kind of a weak acid problem, a Ka type problem, to sort of begin our titration here. Any questions on that there? All right, so we now have our weak acid, we have our initial pH. Now let's talk about what happens as we start our actual titration in this case. So if we are going to come here to number 2 and actually start our titration to before the equivalence point. So let's see what happens there. So we are now going to be anywhere before the equivalence point. And obviously, in this case, we have started our titration. So we are going to get a reaction between, obviously, in this case, the sodium hydroxide and the acetic acid. So we will get a reaction here of sodium hydroxide plus some acetic acid. And this is going to give me a little sodium acetate and some water here. Again, double displacement type reaction sort of occurring here. Now, this again is what we are adding. This is what we are starting with. So since we are obviously adding volume in this case, we will need to use moles. And again, we're going to just make up some numbers like I did last time. So I'm going to say we're going to start with 4 moles of acetic acid. And again, I just made up that number, obviously. And because we are before the equivalence point, as we talked about last time, the moles of my sodium hydroxide should be less than, equal to, or more than the moles of my acid in this case. They should be less than, right? Because again, at the equivalence point, they're equal. So if we're not quite there yet, whatever we're adding is going to be less than our acid. So again, I'm just going to make up the number here of 2 moles, and this would be 0. Once again, at this point, because we are not at the equivalence point, the sodium hydroxide is kind of like the limiting reagent. The excess reagent is our acid, which we have plenty of. And that means that the change in this particular case will be the moles of the base. So -2, -2, and +2 moles. That means that at equilibrium, we will have none of our sodium hydroxide. We will end up with 2 moles of this guy, and we will end up with my 0, and I guess 2 moles, that guy. All right, so just like kind of normal here, super good practice to convert this back to molarity at this point. So again, we would divide by our total volume. And again, that is basically the volume of base added plus the volume of the acid you started with, right? And we'll divide both of those by that, and we'll end up with getting back to molarity. First off, is there any questions on the table here? So if you're not sure how you should get the pH at this point, remember that you can always use your ice table. And if we take a look at our ice table, we see we have this guy left over and we have this guy left over. So the first thing we want to look at is, are they related to each other, these two things? That's acetic acid and sodium acetate. Are they related? They are, right? Acetic acid and acetate is a weak acid and this conjugate base. So this is basically our weak acid and the salt of its conjugate base. And if you have a weak acid and the salt of its conjugate base, that's also known as a buffer. Yeah. So we actually just created a buffer here in this situation. And that means because it's a buffer, you do have 2 options. Probably the easiest option would be to use the Henderson-Hasselbalch equation in this point. Or you could do a second ice table, just like we talked about when we were doing buffers with acetic acid, and have an initial on both sides. That's the important part there if you choose the ice table and not the Henderson-Hasselbalch in this case. First off, any questions on that there? So before the equivalence point in this type of titration, you will actually create a buffer, and you actually make a buffer. And this illustrates that you can absolutely make a buffer from a reaction of a strong base with a weak acid. So you could take a strong base and a weak acid and react them together, and you will then make a buffer. Yeah. So as I mentioned before, you cannot have a buffer that's actually made out of a strong acid or strong base, but you could actually use a strong acid or a strong base and react it with either a weak acid or a weak base, and you could actually make the buffer. So in this reaction, as you can see, to illustrate the making of this buffer, none of the strong base is still there at the end, right? So the result of that reaction actually makes the buffer, and it's like making the buffer in vitro in the beaker by itself through this reaction. Any questions on that there? So what we see there is we start to make a buffer here. So we don't get a dramatic sort of rise here. You do have some buffering action happening as you come through here. But as we also talked about with a buffer, right, you can blow through your buffer, right? So in this case, we're going to kind of blow through our buffer as we near the equivalence point because we are consistently adding at this point base before the equivalence point, which means we're going to make that buffer, which has, as we know, an acid part and a base part. But once I continue to add base to this, it is just going to start to eat up my acid part of my buffer, right? And at some point, I'm going to blow right through the buffer I made. And that is right about there, right? You can start to see a rise in pH and a big jump to the equivalence point here. So you're going to kind of make the buffer, which will kind of keep your pH not rising a lot because you kind of have a buffer, but because in a titration, the goal of the titration is you just keep adding. So you're just kind of blowing through your buffer, and at some point you will blow through the buffer and you will see that big jump in pH until you reach the equivalence point. Any questions on that there? All right, so then let's talk about number 3 here, which is what happens when we do reach the equivalence point here. So we are going to hit the equivalence point of this type of titration. And when we hit the equivalence point in this type of titration, we obviously are going to still have our reaction. So we have our sodium hydroxide, again, in this example, reacting with acetic acid. So again, we are adding this guy and we are starting with this guy, making a little sodium acetate and some water. So once again here, we will need an ice table. And again, we do have to do it in moles since we're adding. So just like previously, I'm going to use my made up starting moles of 4 for my acetic acid. So if I am at the equivalence point, how many moles of sodium hydroxide should I have? I should have 4. It should be equal, right? So that's the definition there of the equivalence point. The moles of the acid will equal the moles of the base. So you should have 4. And as we talked about with the previous titration, sometimes they will not tell you, again, the volume to reach the equivalence point, and you will need that information along with your calculation that you're doing. So again, there's multiple ways you could kind of figure it out. If it's a 1-to-1 relationship between the acid and base, you could use M1V1 equals M2V2. One of those things are the acid, the other one's the base sort of information. We also know that just like we figured out right here in this table, again, that the moles of the sodium hydroxide should be 4. You most likely will also know the molarity of the sodium hydroxide. So you could just use the molarity equation or formula as well, because at that point you will know the moles and you'll know the molarity. You can figure out the volume that would be necessary to get you there. So again, there are multiple ways you could sort of figure out the volume to reach the equivalence point. And again, sometimes they're not sort of given to you. We will start with 0 here. At this point, the good news hopefully is you shouldn't pick the wrong number because there's only one number to pick, and it has to be 4 in this case, yeah? So the change is going to be 4. We're going to go plus 4 in this case. That means at equilibrium, we're going to have no sodium hydroxide left. We'll have no acetic acid left, which is what we would expect to occur at the equivalence point. we will have 4 moles of this guy. We are definitely going to want to convert this back into molarity using our total volume and get our molarity. Any questions on the table here? Again, we could use the table to hopefully understand what's going on at this point, and what I have left at this point is sodium acetate, yeah? And sodium acetate is a salt, and we have our salt and water left over. So at this point, the only thing we have left over is a salt and some water. And whenever we have salt with water, there is something that should come to your head like, does this thing go through hydrolysis, right? So this is what we want to know is, will it react with water at this point? So this salt, right, is basically a sodium ion and an acetate ion. And we should hopefully know, right, sodium, which is group 1, is a neutral salt, right? Because it really came from this guy here. And the acetate, though, came from acetic acid. And since acetic acid is a weak acid, will acetate go through hydrolysis? The answer is yes, it will, because it will act as a conjugate base that's relatively strong. So what happens at this point in the titration is it is not a pH of 7 like it was previous, because all we had left previous titration was a neutral salt. We actually do have a salt in this case that will go through hydrolysis, which means not one ice table at this step, but it is a double ice table situation. You will then need to take that salt that you just figured out and react it with water. And again, because that salt comes from an acid, it will act as a base when it reacts with water, which again means the Bronsted-Lowry definition of a base is it will accept the H plus here. So we will get the H plus being accepted, and we will produce, and it will always happen where it came from. So we'll produce basically acetic acid, and it will produce hydroxide in this case. By the way, before I finish my calculation, I should already know my answer should be basic, yeah, because we are producing hydroxide, right? I also know when I do my calculation, what type of K value do I need? KB, yeah? I most likely only have a Ka at this situation, right? So this would be a situation where Kw might come in handy, yeah, to convert our Ka into our Kb value here to use it in the calculation. So our initial here is going to be our equilibrium concentration from above. So that guy is going to come right on down over. And now this table is going to be just a regular table with some zeros and X's. This will go into, as we just talked about, our KB expression. You can make an assumption, whatever you'd like to do on that. You will solve for X. It is also important to remember in this case, though, when I do solve for X, it equals the hydroxide concentration. So this will equal the hydroxide concentration, which means you got to probably go POH first and then to pH. Yeah. So a little bit more work at the equivalence point in this type of titration than the first one, where you could just write 7 and be happy and done and not do any calculation here. This is, again, a double ice table situation. The whole purpose of the first ice table is to figure out what is the concentration of your salt that's left over that will go through hydrolysis. This is also why it's super important just to make sure you convert this back to molarity when you're done with that first table, because if you roll with moles here and forget to incorporate the volume, you're going to be in trouble at the end of the second calculation. So again, like I said, even though we talked about that you could roll with moles with the Henderson-Hasselbalch equation and it will work out okay, it's just really good idea just to convert it back to molarity in case you're not doing buffer and Henderson-Hasselbalch. You'll have it in the correct units and everything will work out correct. Any questions on that? So in this type of titration, when you hit the equivalence point, you will always have a salt that will go through hydrolysis because it came from a weak acid. And because of that, it will always produce hydroxide, and you'll have a basic pH at the equivalence point in this type of titration. As we could see here, at the equivalence point, it is not a pH of 7 in this titration. It is a pH of 8.7, yes. Hence why, by the way, this is the titration you typically use your phenolphthalein for, because it works between like 8.3 and 10. Also why they yelled at you like, hey, stop around this first color of pink that you see, to try to keep you at that 8.3-ish range, 8.7-ish range, which is typically probably where you would end up in terms of the pH in that case. Any questions on that there? All right, so let's take a look at the fourth part, which is it turned pink, didn't stop you. You're going to keep going. So we're going to go past the equivalence point in this case. So again, going past the equivalence point here, we obviously are going to get a reaction between our sodium hydroxide and our acetic acid. So again, we are adding the sodium hydroxide. We are starting with this, and we're going to use our made-up numbers like normal. So we're going to go with 4 moles here of our acid. Now, clearly, we are past the equivalence point in this case. And that means at the equivalence point, the moles of the acid and base are equal. And if we keep adding, we now should have more moles of what we added than what we started with. And again, I'm just going to make up the number of 6 moles in this case, and we'll have 0. So what happens as we go past the equivalence point is we do get a change in what is the limiting reagent, the excess reagent at this point. Since we have less moles of our acid, it is like the limiting reagent. And now we got plenty of moles of sodium hydroxide because you just keep adding it from your burette. So the change here should be the acid, the smaller number, yeah, -4, and +4 moles here. That means at equilibrium, we will end up with 2 moles, 0, and 4 moles at this point. Like normal here, we're going to throw everybody back into molarity by dividing by our total volume. And now, again, we could kind of use our ice table to help us understand what we got going on at this point. So we got a little sodium acetate, and we got a little sodium hydroxide. Are these two things related to each other in a buffer sense? Are these guys a buffer? The answer is no, they are not a buffer. Yes. So you should not, again, as we talked about last time, because you end up with 2 numbers, decide, hey, I want to roll with the Henderson-Hasselbalch equation because I got 2 numbers. Seems like a good idea. Seems like a terrible idea in this case because you will get it wrong because it's not a buffer. So what do we have? We obviously have a salt, as we saw at the equivalence point, that will go through hydrolysis and act as a base. And then we also have sodium hydroxide, which is a strong base, right? So between the salt, which is acting as a base, and our sodium hydroxide, which one is the major contributor here of hydroxide to the solution? It is going to be the strong base, right? So the sodium hydroxide just needs to go for a swim, and you add it, and it's going to produce hydroxide, right? It's just going to break apart. The salt there has got to go find some water, right? Do a little reaction and to produce that. So although the salt is obviously producing hydroxide, it is definitely not going to be the major contributor to hydroxide in this reaction or this solution at this point. So what we typically do is we ignore the contribution of the salt at this point, and we roll with the strong base, which again is going to be really the major contributor here of hydroxide in the solution. And because that is a strong base, that means that you will have the hydroxide concentration. And because you have the hydroxide concentration, you can get the POH. and then you could get to the pH in this case. So past the equivalence point in this type of titration, again, you're really just adding base to your solution, and you need to basically figure out the concentration of your strong base that's left over, which will give you really your hydroxide concentration and allow you to go into the POH equation and then again into the pH equation. Any questions on that there? So you can see here this titration curve a little bit different, a little bit different than the one we saw previously. You need one ice table here for a Ka type of problem. Here you need at least one ice table, and you're going to end up with a buffer. Here you have some hydrolysis and a salt going on, and past it, you really just have a strong base. So a lot more calculations involved in this type of titration. It is, again, really good to sort of know where you are in the titration curve because you could kind of figure out what type of calculation you should be doing. Like if you know you're before the equivalence point, you know you should end up in a buffer. You know, if you're at the equivalence point, you should be doing hydrolysis. If you're starting out, it should just be like a Ka type problem. So sometimes it's good to take a moment and try to figure out where you are in the titration, and it will help you with the rest of the calculation because you kind of should know what should be going on at that point. All right, why don't we try one here? Let's do all right, so what is the pH after 23 milliliters of 0.1 molar sodium hydroxide is added to 25 milliliters of 0.1 molar acetic acid? Ka of acetic acid is 1.8 times 10 to the minus 5. All right, so take a few moments there, calculate it up, see what you end up with. Okay, let's take a look at it here. So this is obviously the same titration we've been talking about. So again, we are adding our sodium hydroxide to our acid here. So we definitely are going to get a reaction since we already added some sodium hydroxide. So clearly we've got our sodium hydroxide here, which is being added to our acetic acid, which we are starting with in this case. Going to give us our sodium acetate and our water in this case. So definitely, since we are definitely started our titration, we want to do this ice table in moles. So we do need to calculate the moles of everybody. So taking our 23 milliliters and converting it into liters, divide by 1,000 or move the decimal point, times 0.1 moles per liter. Our liters are going to cancel, and that's going to get us our 0.0023 moles of sodium hydroxide. Do the same thing here for acetic acid, 0.025 liters times its molarity, 0.1 moles per liter. Again, the liters here will cancel, and that's going to get us here 0.0025 moles of acetic acid. So those are our initial moles here. So initially here we got 0.0023 moles, 0.0025 moles, and 0. So at this point, we can definitely determine where we are at. Am I before, at the equivalence point, or after the equivalence point in this case? I am before the equivalence point, and I know that because the moles of what I'm adding is less than the moles of what I'm starting with. So I know I haven't reached the equivalence point yet. Otherwise, those guys would be equal, right? And I'm not past the equivalence point because the moles of what I'm adding is still less than what I started with in terms of the acid. So the change here will be our moles of our sodium hydroxide plus 0.0023 moles. At equilibrium, again, we end up with none of the sodium hydroxide. We will end up with here, if I hit the right buttons, maybe. Looks like 0.0002 moles and 0.0023 moles. At this point, as we talked about, we do want to convert back into molarity. So our total volume at this point was, we started with 25 of our acid. We added 23 milliliters of our base. That's 48 milliliters at this point. So we do want to divide these guys by 0.048 liters. Again, we want to convert it into liters in this case. And that's going to get me here. Looks like 0.00417, we'll call it, and 0.0023 divided by 0.048. Looks like 0.0479 molar. First off, any questions on the table? So by knowing I am before the equivalence point, I should already know the answer to my next question, which is if we look and see what is left over at this point, we do have acetic acid and sodium acetate, which should give us the buffer that we would expect before the equivalence point in this type of titration. So we do have a buffer that is made as we would expect, which means we can go into our Henderson-Hasselbalch equation here to get the pH. And again, the pKa value will be minus the log of 1.8 times 10 to the minus 5. That's a 4.74 for acetic acid. So putting that in, 4.74 plus the log. We do want the base, and this guy, which is acetate, has one less hydrogen, and it is the base. So that's going to go up on top. And on the bottom will go our other one there, where I lost it. There it is. Wow. So if we do that 0.0479 divided by 0.00417, take a little log action of it, add it to 4.74, and get us somewhere in the ballpark of 5.8 since I used to rounded guys there. Any questions on that there? Let's see how we did. I think this is the same titration that's in this table. So 5.8 is between those two numbers. So that's not bad. I guess we're in line with where we should be. Any questions on this type of titration? So again, as we've been talking about, it is important to know what type of titration you're doing and where you are, because again, it is different depending on what you're titrating with and where you are located. Any questions on that there? Yeah. First off, in this type of titration of a weak acid and a strong base, you will always have a buffer before the equivalence point being made. So just knowing you're before the equivalence point, you should know that you should end up in a buffer situation. Secondly, if you weren't sure of that, when you're done with your ice table, you take a look at your ice table, you basically have this guy left over and you have this one left over, and that is acetic acid and sodium acetate, and they are related to each other based on the Bronsted-Lowry definition of a weak acid, which is this guy, and its conjugate base, which is this guy. And it's not really the sodium part here, it is the acetate part, right, that makes them related to each other by 1H plus in this case, yeah. And that is basically how you know you have a buffer left over. Yeah. Other questions? Okay, we'll lay it up there for